Okay, hello everyone, it's Salar and welcome back to this tutorial. In part 8 of this tutorial, I wanted to start to talk about semaphore, as I said in previous part. So, in this tutorial, we wanna know how can we use OTP RTOS in STM32 cube ID. But let's describe to you what is semaphore. What is semaphore? What is semaphore? Before to start talking about what is semaphore, let's see what is context switch in the RTOS. What's context switch? Assume you created 4 threads, thread 1 and thread 2 with priority high, thread 3 and thread 4 with priority low. And this is the timeline of the processor. After starting the RTOS, the operating system runs thread 1 for 1 millisecond. For this time slice. After 1 millisecond, stop running thread 1 at this point and start to running thread 2. This changing from a thread to another thread called context switch. Okay, another time for 1 millisecond run thread 2, another time you have context switch and return to thread 1. Doesn't run thread 3 and thread 4 because thread 3 and thread 4 have lower priority than 1 and 2. And I said when you have some threads with higher priority than others, the operating system just runs these threads. But if you wait or suspend these 2 threads, the operating system can run the other threads with lower priority. Okay, another time for 1 millisecond, thread 1, another time context switch, jump to thread 2, run for 1 millisecond, stop it, and thread 1 and thread 2, and so on. Okay, so stop the running of a thread and jump to the next prior thread called context switch. Okay, the operating system does this work automatically. Now, to describe what is semaphore, consider these examples. Another time, assume this is the thread functions of thread 1 and thread 2. Okay, in thread function 1, you want to do some jobs, and after that you want to print this string in output in terminal by using of serial port. Okay, assume this function does these jobs and now it wants to print this string. It wants to print T, H and the rest of the string, but assume at this time after printing T and H you have context switch and operating system jump to the next prior thread. You have, for example, context switch and operating system jump to the next prior thread. Now this function wants to use printf like thread function 1. Serial port and printf is a resource, okay, and shared between thread function 1 and thread function 2. Now the thread start to printing this string. Another time T, H, thread 2. Okay, and a \n, enter, and go to the next line. And after 1 millisecond, another time the operating system return to this point. To run another parts of this thread and start to printing rest of this string. Read 1 and enter. But I wanted to print this value, thread 1, and after that thread 2, but the operating system and prints this value in the output. This problem called conflict. We have a conflict between thread function 1 and thread function 2 because printf and serial port shared between thread function 1 and thread function 2. How can I get rid of this problem, this conflict? When I want to use printf and serial port, I need to lock that. Let's to see a pseudocode. Assume at this time I've changed the thread function 1 and 2 to these codes. I have a first while loop here. Okay? I want to use printf. I want to use serial ports. First, before to using printf and serial port, thread function 1 needs to lock serial port for itself. By using of this function, I will say you how you can implement this function. But at this time, if serial port or printf is free and has not been used by other threads, thread function 1 can lock serial port. If the return value is okay, this means that serial port has been locked by thread function 1 or thread 1. Now thread 1 can use printf. And after using this resource, it must unlock serial port another time and break from this while loop and go to this infinite while loop. Okay, now another time, assume serial port is free and is unlocked. If the serial port value was unlocked, the value of lock serial port is okay. Now thread function 1 can use printf. Another time, assume after printing C and H, you have context switch and thread and operating system jump to thread function 2. But at this time, another time thread function 2 needs to acquire serial port, but at this time the return value of this function is error because serial port has been acquired by thread function 1. Because the value of the return value of lock is error, the function doesn't run this if block and do thread yield. By using a thread yield, you can have an early context switch. Okay, by thread yield you have another context switch and return to this point. Print rest of the string, thread 1 and backslash n to the next line. Now unlock the serial port. Now unlock the serial port. Another time serial port has been unlocked and break this if block this while loop and jump to this while loop. Another time, after 1 millisecond, you have a context switch to this after thread yield, another time to the startup while loop. Back to the startup while loop, another time thread function 2 wants to acquire serial port. But because serial port has been unlocked here. Now the return value of lock is okay, and it can print this value, print thread 2 and \n, and another time unlock and break and go to this file. Okay, so by using this locking mechanism, lock and unlock function, you can lock a shared resource. Serial port at this time is a shared resource to prevent conflict. Okay, to prevent conflict, you must use locking mechanism when you want to use shared resources. But how can I implement this locking mechanism? Assume the locking mechanism is just a variable, a semaphore. When the value of semaphore equal to 1, it means this resource is unlocked. But when the value of semaphore equal to 0, this means the resource has been locked by a thread. So when you want to use printf, you can use this variable, this global variable. If the value of semaphore is 1, this is unlock. This means unlock. Do semaphore minus minus, lock the semaphore. Now the value of semaphore is 0. Use shared resource, and another time change the value of semaphore to 1. Okay, change the value of semaphore to 1. Another time unlock it. Okay, and break. If the value is unlocked, lock it by semaphore minus minus, or put 0 in semaphore. Use the shared resource, and after that unlock it. Another time put 1 in semaphore. Okay, in this way, this easy way, you can implement a semaphore. But implementing the semaphore is much more complicated than this example. Okay, but in this example, I want to show you what is the concept of implementation. Okay, but implementation of semaphore is much more complicated. If you want to know how you can implement semaphore, refer to my YouTube channel and RTOS playlist. Okay, by using RTOS tutorial, you can find out how you can implement semaphore in the RTOS. Okay, but this is semaphore count value. Okay, this is semaphore count value, 1 or 0. The maximum value is 1. Okay, this value called semaphore count. Okay, semaphore count. The semaphore count shows the state of a resource. Okay, if it's 1, it's unlocked. If it's 0, it's locked. But semaphore count can be more than 1. But why? Why we need to have semaphore count that is more than 1? As I said, serial port is a resource, and threads want to use serial port to send some information to other boards and computers and so on. Okay, but you may have 2 or more serial ports on your board. Assume you have, for example, 2 serial ports on your board. When a thread wants to use serial port, it can acquire one of the. Okay, assume you have 2 serial ports on your board. when a thread wants to use serial port, it can use one of them. At this time, semaphore count shows the number of resources. Let's give you an example. USB port can be a resource. Assume you have 4 USB ports on your board and threads in your project wants to use USB ports. I can control USB port as a shared resource by using a semaphore count. When semaphore count equal to 4, this means you have 4 free USB ports on your board. When semaphore count equal to 3, this means you have 3 free USB ports and one of them used by one thread. When this value is 2, this means you have 2 free USB ports. When this value is 1, this means you have just 1 free USB port, but when the value is 0, this means you have no free USB ports. And all of your USB ports have been used by threads. Okay, at this time, semaphore count shows the number of free resources. Okay, at this time, the maximum count is 4 because I have 4 USB ports on my board. So, how can I implement this countable semaphore? In this way, if the value of semaphore is greater than 0, okay, greater than 0, for example, is 1, 2, 3, 4. This means you have at least 1 free USB port. Semaphore minus another time to acquire a USB, for example, to acquire a resource. At this time, assume semaphore count shows the number of serial ports, the count of serial ports. After using the resource, you can increase the value of semaphore count to return the semaphore to the RTOS. For example, assume the value is 2, you can use one of the semaphore. Now the value of semaphore count is 1. Another time you must return the semaphore. Do semaphore plus plus, and another time the value of semaphore is 2. But if the value of semaphore is equal to 0 or greater than 0, this means you have no USB ports or no resource and you can use your resource. Okay, so now you know what is semaphore. Semaphore is a locking mechanism. Semaphore is a locking mechanism. When you want to use a shared resource, you need to lock and acquire that resource. Then the maximum when the maximum count is 1, it's called binary semaphore. But when the maximum value is greater than 1, it's called semaphore or countable semaphore. Okay, this is the concept of semaphore. Semaphore is a locking mechanism. Okay, it's a locking mechanism. By using a semaphore, you can prevent to happen conflict between threads. this is one conflict. Okay, I said because printf shared between thread 1 and thread 2. Okay, very good. This part was about concept of semaphore, but in the next part I will show you how you can use semaphore in the Untitled project RTOS. Thank you very much to see me, and see you soon in the next part.